Yeah, you guys are doing okay so far? Easy. Did you guys start the online assignment?
Yeah.
Like a review thing?
Yeah. Oh yeah, it's just the website. Yeah, website.
I think the problem is because I have a lot of problems there. That's why it's taking too long. But after this one, all the assignments will be smaller, and you don't have the same problem. So try to do as much as you can in one sitting and submit.
That's due Sunday, right?
Yeah, I haven't really changed the date yet, but I'll do that today. Okay. Okay, so last time I think I ended with this, the graph of a function f. So what do we mean by the graph of a function? Well, for every x or for every input in the domain of f, you pair up the input with the corresponding output, and you get an ordered pair. And so you look at all such pairs. So you get the collection of all pairs of the form x f of x, and that's the graph of the function. And how do we visualize the graph? Well, what we do is that we plot each of these points on the plane, and the collection of all these points. The plot of all these points will give you a curve in the plane, and that's the graph. Okay, so let me start with let me go over a couple of examples today. Let's look at the function f of x is equal to c. So here c is a constant. C is a constant here, and so what is this function? This function is the output value for any given input is c. Okay, so what would be the graph? Well, the graph would basically be a horizontal line, right? So let's say this is the x-axis, this is the y-axis, this is the origin here, and let's say c is a negative number, so c is right here, let's say. Then the graph of this function is the horizontal line going through the point 0c. Again, the reason is for any given x, the corresponding output value is c. Okay. Is everybody okay? So the height of the graph at any given x is c. All right. So how about the graph of let's say so this is the graph of y equals to c, right? The graph of f of x equals to c is the same as the graph of the equation. The graph of the equation y equals to c. Another example. Let's say I have the function f of x equals to x, and what's the graph of this function? The graph of this function, well, we know that the graph of this function is the same as the graph of the equation y equals to x, and the graph of that equation is a straight line. We know that. And how do you draw the graph of a Straight line, all you have to do is pick 2 points on the line and add them in a straight line. So for this one, if x is 0, then y would be 0 as well. If x is 1, y would be 1 as well. So what you get is a straight line like this. And let's say this is a 1 here, this is 1 here, oops, this is a 1 here, so this is the point 1, 1. If I pick another point, let's say here, let's say the corresponding input value is x, then what's the output value? This point is what? X and x. Okay, so the graph of this function is just that straight line. So the height at any x is x, right? The height at any x is x. Another example. Let's say I have the function f of x equals to 2x plus 1. And so the graph of that is the same as the graph of the equation y equals to 2x plus 1. And in this case, the graph would be again a straight line, but now what's the slope of this straight line then? 2, and intercept is 1, right? So again, how do I draw a straight line? I just pick 2 points, right? So when x is 0, I get 1, right? So let's say the point 1 is right here, and then when x is negative, well, when x is 0, I get 1, and let's pick when x is negative 1, what do I get? I get negative 1, right? No. When x is negative 1, negative 2 plus negative 1, yes. So when x is negative 1, right here, then I get negative 1 as well. So let's say this point here. So the straight line that I get would be this straight line here. Whoops. Okay, so this is the straight line that I get by just joining those 2 points, okay? And I should be, of course, extending to the other side of this point as well. Okay, so that's the graph of this equation. Everybody's okay with that? Okay. Let's look at another example. What's the graph of f of x equals to x squared? Well, that's the graph of y equals to x squared. And I'm pretty sure all of you know what that is. So this will be what? It'll be a parabola. So if this is 1 here, the height at 1 would be 1. Height at negative 1 would be 1 as well. So this is 1. And basically, you get a parabola like this. So that's the graph of this function. What if instead of x squared, I have root x? The graph of this function would be the same as the graph of the function the graph of the equation y equals to root x. And what's the graph of that? The graph of this function is what? First of all, notice that what is y squared then? x. So what's the graph of the equation y squared equals to x? That's a parabola going to the right, right? So basically what you get is something like this, and another part like this. Now the blue part is basically the graph of the positive root of x. So from the equation y squared equals to x, if you solve for y, you get plus or minus root x. Okay, so this the other side is the graph of negative root x. Okay, so together it's the graph of the equation y squared equals to x, but separately one of them is the graph of the function root x, the other one is the graph of the function negative root x. Is everybody okay with that? Okay. Example. What's the graph of the function f of x equals to absolute value of x? Well, that's the same as the graph of the equation y equals to absolute value of x. Now notice that absolute value of x is so we can write this in the following way. So y is basically the same as x as long as what? X is non-negative, right? Because if x is non-negative, absolute value of x is x. But if x is negative, right? If x is negative, then what is absolute value of x? Negative x, right? If x is already negative, how do you make it positive? You multiply by a negative sign, right? So you get negative x. Is that making sense? So what's the graph of this function then? Well, what you get is the following. Let's say I have my x-axis and y-axis here. And first of all, what's the graph of the equation y equals to x? What's the graph of y equals to x? Well, that's just a straight line, we know. So let's make that. And so this is y equals to x. And what's the graph of y equals to negative x? That would be the other way. Okay, and so this is the y equals to negative x. However, y equals to x when x is positive only, so that means I have to erase which part? The bottom parts here, and also this part here, because the function is given by negative x only when x is negative. So you delete the part to the right of 0. So at the end, my graph is basically this V-shaped graph. Is that okay? All right. One more graphing example here. Suppose I have a piecewise defined function. So what do I mean by that? Well, it's basically what we did in the previous example. The function is given by the formula 1 minus x if x is larger or equal, if x is less than or equal to negative 1, and it is given by the formula x squared if x is larger or equal to, larger than negative 1. Okay, so what's the graph in this case? Well, again, let me make my favorite xy plane, and y-axis. Okay, so what do? Well, I basically draw the graph of 1 minus x and the graph of x squared and delete the parts according as the values of x, okay? So what is the graph of 1 minus x? Well, the graph of 1 minus x is a straight line. So when x is 0, you get the point 1 right here. I keep doing that, so I'm allowed to only make one line, I guess. Okay, so the graph of 1 minus x can be found by just plotting 2 points. When x is negative 1, right? When x is negative 1, the value is 2. So I get this point here. So what's the straight line? The straight line is basically like this. Okay, at 1 the value of the function is 2, so this height here is 2. Okay, that's very well. Now what's the graph of x squared? The graph of x squared is a parabola, we know. At negative 1, what's the value of the parabola? 1. But I need a hole here because the function is not defined there by x squared. And then at 1 the value is here, so I get a parabola like this. Now the graph of the parabola of course goes like this here, but we don't take that part because when x is less than negative 1, the function is defined by the 1 minus x. We also have to delete what? We also have to delete this part, right? So that's the graph of this function. When x is less than negative 1, it's given by the straight line. When x is greater than negative 1, it's given by the parabola. Is that making sense? So how do you draw a piecewise defined function? Well, you draw the graph of each part, and then you delete the parts that are not necessary, right? Is that okay? Okay, so that's the piecewise defined function. Okay, so now I want to give you some definitions here. So a function f of x is said to be an even function. Is an even function if the value of the function at negative x is the same as f of x for all x. So what this is saying is that the value of the function at x and negative x are the same. For example, the value of the function at 1 and negative 1 are the same. The value of the function at half and negative half are the same. Another way of saying that is that if I look at the graph of the function f, the height of the graph at x and negative x are the same. The height of the graph of f at x and negative x would be the same, right? So if you have an even function, if you have an even function, what happens is that is the following. Let's say I have a point, this point here, let's say this point is x comma y. So let's say this is a point on the graph of this function f, and f is even. Then the graph of f will also have another point which is symmetric about the y-axis right here, and this point would be negative x comma the same y. So if you have an even function, whenever xy is on the graph of f, negative xy is on the graph as well, right? So the graph of f at x and negative x, the height of the graph of f at x and negative x would be the same. Is that making sense? The heights of the graph at negative x and x are the same. You guys agree with that? So if I have an even function, it means that whenever xy is a point on the graph, negative xy is also a point on the graph. Okay. So for example, we just did an example here with the function x squared, right? Notice that the function x squared is an even function, right? Why? Because if I look at f of negative x, right, for this function, what is that? Well, that's square of negative x, and square of negative x is the same as square of x, and that's exactly the same as f of x, right? So notice that the graph of f is symmetric about the y-axis, and this is precisely because it's an even function. So whenever you have an even function, the graph of the function is symmetric about the y-axis. You can remember that. Okay. And then, well, since I use the word even function, you can imagine that there is an odd function. So what is an odd function? F of x is an odd function if the value of f at negative x is negative of f of x. So what is it telling you? It's telling you the value of f at negative x and x, they are opposite of each other in sign, right? The value of f at negative x and x, they have opposite signs, right? So in other words, what that means in terms of the graph is that if I have a point, let's say this point here, and let's say this point is x comma y, so here is x. If xy is on the graph of an odd function, then negative x and negative y will also be on the graph. So the point, let's say this is negative x and then negative y. So let's say this is the point negative x, negative y. Negative y. So if xy is on the graph, negative x, negative y is also on the graph. And what happens is that these 2 points are at the same distance from the origin. Okay, so if I join these 2 points, I'll be going through the origin. Okay, so the distance from here to here is the same as the distance from here to here. So the graph of an odd function is symmetric about the origin. Okay, the graph of an odd function is symmetric about the origin. So again, odd function means whenever xy is on the graph, negative x, negative y is also on the graph. So the height of the graph at negative x and x, they are opposite of each other. The height of the graph at negative x and x, they are opposite of each other. Is that okay? Alright, so that's what we mean by an odd function. So one example of an odd function would be the following. Let's make a xy plane again. And one example of an odd function would be the graph of x cubed. Okay, so if I can make it nicely. So this is let's say this is the graph of x cubed, and this function is an odd function because the height of the graph at x and negative x, they are opposite of each other, right? What's the height at negative x? It's negative x cubed. What's the height at x? Is x cubed, so which are negative of each other. Is that making sense? Okay, so this is an odd function. So let me just write down odd. So other examples of even and odd functions. Suppose I have the function f of x equals to x to the 5 plus x. Is this an even function or an odd function? So how do I check it? Well, to check that whether it is even or odd, all you have to do is calculate f of negative x. And what is f of negative x? It will be negative x to the 5 plus negative x. So you replace x by negative x. And notice that negative x to the 5 is negative x to the 5 and minus x. And then if you factor out the negative, you get x to the 5 plus x. And that's exactly the negative of f of x, right? So I see that f of negative x is the opposite of f of x. So this is odd. So f is an odd function, right? Again, if you have an odd function, it means that the graph of the function is symmetric about the origin. Another example. Suppose I have the function g of x. It's given by 1 minus x to the 4. Okay, so what is g of minus x? It's 1 minus negative x to the 4, which is exactly the same as 1 minus x to the 4, which is g of x. So g is what? G is even. Well, can you have functions which are neither? Can you give me an example of a function which is neither? Neither even nor odd.
X cubed plus x squared.
Yeah, it's a very good example. X cubed plus x squared. Notice that if I have h of negative x, that's going to be what? Negative x cubed plus negative x squared, which would be negative x cubed plus x squared. And this is not equal to h of x for sure, right? And it is neither a negative h of x, right? It's not h of x, it's not negative h of x either. So h of x is neither even nor odd. So h of x is neither even nor odd. Is everybody okay with that? Okay, so one of the things that I forgot to review about functions is the vertical line test. Let f of xy equals to 0 be an equation in x and y. What do I mean by f of xy? I mean that f of xy is some sort of expression in x and y. It could be x plus y, it could be x squared minus y squared, it could be root of x plus y. Okay, so this is f of xy here represents something in terms of x and y. And so you have an equation involving x and y. So whenever you have an equation in x and y, it has a graph. Okay, the question is whether the graph of the graph of an equation in x and y represents a function. How do I determine whether the graph of an arbitrary equation is a function or not? Well, let me explain that by using some examples. If I have this equation y squared is equal to x, right? This is an equation involving x and y, and it has a graph, and we know that the graph looks like the following. This is the graph of this equation, and the question is, does this graph represent a function? Well, it doesn't, and vertical line test means that if you make a you need to check whether there is a vertical line that intersects the graph at more than one points. And we see that, yeah, there are plenty of them. That if this vertical line, for example, let's say this number is x here, then I see that the vertical line intersects the graph at more than one point. Okay, so this point here is x comma root of x, and this point here is x comma negative root of x, for example. Okay, and so this does not represent a function. Same way, if I draw the graph of graph of a circle, right? The graph of a circle, it doesn't represent a function either. Okay. So what is the vertical line test to determine whether a given curve represents a function? Well, yeah, go ahead. Yeah. So the way you want to say it is that the graph of an equation represents a function if every vertical line intersects the curve at most at one point, right? The graph of an equation represents a function if every vertical line intersects the graph at most at one point, right? Then it's a function. Otherwise, it's not a function. So if you have at least one vertical line that intersects the graph at more than one point, then it's not going to be a function. Is that clear? You can remember that? Okay. So that's the vertical. So this is not a function by the vertical line test. So not a function. More precisely, what I should be saying that this graph does not represent y as a function of x. You cannot think of y as a function of x. However, notice that if I switch if I sort of view this graph from the other side, I can think of x as a function of y. You agree with that? So if I look at it the other way around, horizontally, right? X is a function of y. I can view it that way, but y is not a function of x. So when I'm saying vertical line test, I'm determining whether y is a function of x, right? I'm not determining whether x is a function of y. Okay. But usually, whenever we draw a function, we draw the second coordinates vertically and the other one horizontally, right? Okay, so input values are on the horizontal axis, the output values are on the vertical axis usually, right? So, okay, so that's it for that. Okay, so what I want to cover is now the operations on functions. Remember, I gave you this. I gave you this handout on graph transformation, right? Please read it yourself. I will probably talk about it a little bit on Monday, but I won't write down everything that I wrote down there. Okay, I'll just go over some examples to explain how they work, but I won't write down the statements that I gave you already. So what I want to cover now is operations of functions. Operations on functions. Actually, first of all, I want to look at the algebraic ones. the algebraic operations on functions. So let's let f and g be functions. So I have two functions, and I'm going to define some new functions by algebraically manipulating these two functions. So one of them is that I have f plus g. So I'm defining a new function, and I'm denoting that by f plus g. So f plus g represents a function. So if I need to define a function, I have to tell you what the function does to an input. So what does it do to x? Well, what it does is that it calculates the value of f at x, it calculates the value of g at x, and then it adds them, right? And if I have f minus g instead of f plus g, then you're going to have a minus here. Okay, so that's what I mean by f plus or minus g of x. 2, what is f times g of x? That is f of x times g of x. So this function basically calculates the values of the two functions separately and then multiplies them. 3, f divided by g evaluated at x, which is f of x divided by g of x. Now in this case I have to put in an extra condition that g of x is not the zero function. So you don't want g of x to be the zero function, otherwise it's obvious that you don't want to have the zero function in the denominator. Okay, so those are the algebraic operations of functions. Let me give you an example here. Let's say I have a function f which is given by root of x minus 1. I have another function g of x which is given by 2x plus 1. So what is the value of f plus g evaluated at, let's say, 5? The value of f plus g evaluated at 5 would be what? Well, you calculate each function separately at 5 and then you add them, right? You calculate each function separately at 5 and then you add them. What is f of 5? 2. And g of 5? 11, which is 13. Okay, what is f over g evaluated at 5? Well, that would be f of 5 over g of 5, which is what? 211. Is everybody okay? But you can also find a formula for f plus, let me use f minus g. So what would be a formula for f minus g at any x? Well, it's just whatever f of x is minus whatever g of x is, right? What would be f times g of x? Well, it will be root of x minus 1 multiplied with 2x plus 1, right? Okay, very clear. Can someone tell me generally, if you know the domain of f and if you know the domain of g, what would be the domain of f plus g? Okay. So does that make sense? So what I want to know is the following: what is the domain of f plus g, or f plus or minus g? If you know the domain of f and g, how do they relate? how does the domain of f plus g relate to the domains of f and g? Well, the f plus g, in order to calculate that, you have to be able to calculate both f and g at x, right? So x gotta be in the domain of both f and g, right? So that means the domain of f and the domain of f plus or minus g would be the domain of f intersected with the domain of g, right? The common domain of the two functions will be the domain of f plus or minus g, right? Whatever the input is, it has to be in the domain of both both functions in order to calculate f plus minus g of x. Is that clear? The same way, what is the domain of f times g? Also, it will be the same, right? As long as x is in the domain of both f and g, you can calculate the product. However, there is a little bit of problem with the domain of f divided by g, right? What would be the domain of f divided by g? Of course, in order to calculate f divided by g, you need x to be in the domain of both, so you still have to have that the x belongs to the intersection of the two domains. But then, what else do I have to do? I have to exclude the values of x where g vanishes, right? So I have to sort of like exclude, so this sign means exclude the values of x such that g of x is 0. Is that making sense? So it's not enough to take just the intersection, you also have to get rid of the values where g is 0. Okay, so that would be the domain of the fraction. So just to give you an example, yes, lower. Okay. Any questions anyone so far? Okay, so what's the in my example here? Can someone tell me what's the domain of f? What's the domain of the function we have here? What's the domain of this function? Zero or 1? 1. Yeah. So because x minus 1 needs to be greater than 0, so x has to be greater than 1. So that's the domain. And what's the domain of g in our case? All real numbers, very good. So this is negative infinity to positive infinity. So then what's the, let me go up a little bit. Then what's the domain of f times g? And what's the domain of f plus or minus g? It will be what? The intersection or the common domain. So what's common between the two domains? Yeah, everything from 1 to infinity, because 1 to infinity is included in the domain of g. So this would be from 1 to infinity. And is it the same for f divided by g? What's the domain of f divided by g? Well, it will be the same as 1 to infinity, except that I have to also exclude where g vanishes, right? However, are there any points where g vanishes there? No. So it will be still the same as this one, because g does not vanish at any of the points between 1 to infinity, right? So suppose that I make a little bit of a change. Let's say, let's make a change. Where do I make a change to sort of not have that one? Yeah. So if I sort of in the definition of g, right? In the definition of g, instead of that 1, if I replace that by a 2. No, that's not enough. If I replace that by a -2, okay, so then G vanishes where? G vanishes at 1 then, right? If I replace that 1 by -2, then I have the function 2x minus 2. So when x is 1, G vanishes. In that case, the domain would be what for f over G? It will be everything from 1 to infinity, but now 1 is excluded, right? Is that making sense? Okay, so that's all on algebraic operations on functions. The next thing that we need is the most important operation on functions, which is the composition of functions. Composition of functions. So let's let f and g be functions. And so what is the composition of the two? The composition of the two functions is denoted by f circle g. So this is not a usual multiplication. And the f circle g evaluated at x. So whenever you define a function, you have to tell what does the function do to an input. And in this case, what it does is that it calculates the function g of x first, and then it applies the function f to that. So that's the definition of this composition function. So you calculate g of x first, and then you apply f to that. So in other words, what you're doing is that you apply g to x, you get a value y, and then you apply f to y, you get a value z, and then basically the composition function is taking you from x to z. Right? The composition function f circle g is taking you from x to z. So whenever you have a composition, okay, the function g of x here, that's called the inner function of the composition, and the function f is called the outer function. Sometimes people would say inside function, outside function of the composition. Okay, is that clear? So let's do an example. Let's say again I have the function f of x equals to root of x minus 1, and g of x is the function 2x plus 1. What is f circle g of x? Well, this is f of g of x. So we first replace g of x by its value, which is 2x plus 1. And then we look at the function f. And what do we do in the function f? We replace x by 2x plus 1. So we get this, and that's basically what? Root of 2x. How about if I look at g circle f? So now we are taking the function in opposite order. So this is g of f of x. Now the inside function is f. What is that? This is g of f of x is root of x minus 1, and this is equal to 2 times root of x minus 1 plus 1. So what do you see? Well, f circle g is not the same as g circle f. Generally, they are not equal. So notice, remark, generally f circle g is different from g circle f. Of course, there are cases when they are the same, right? For example, if f and g are the same functions, right? When you take f circle f, that's the same as when you take them in opposite order, right? Okay, so that's what we mean by composition of functions. I'm going to do more examples on this on Monday, and then move on to other things. Once again, don't forget your online assignment due by Sunday, and I'll see you on Monday.